So I would like to present some technical aspect of our coupled atmosphere-ocean data assimilation that is being developed at Environment and Climate Change Canada. So first, I acknowledge my colleagues. So it's a brief outline of my presentation. Our weekly coupled assimilation system is built on the data assimilation components and the forecast component that are used operationally, and I'm going to briefly describe this, their current state. Then some important technical coupling issues will be highlighted, then we move to conclusions and perspectives. The atmospheric part of our coupled data assimilation system is called Global Deterministic Prediction System, GDPS, which is operational atmospheric data assimilation system. The GDPS is built on the global environmental multi-scale GEM atmospheric model with a horizontal grid spacing of approximately 25 kilometers on a yin-yang grid. This is a staggered hybrid log pressure vertical coordinate model with 80 vertical levels, and the model top is around 0.1 hectopascal. For operational NWP, the GEM model is used in a coupled mode to compute every day 10-day coupled atmosphere ocean CICE forecast. And GEM model is used in an uncoupled mode to compute 6-hour background state for the atmospheric data assimilation. But in the weekly coupled data assimilation system, we also run GEM in a coupled mode, like in the forecast mode to compute the background states. The GDPS data assimilation method is a hybrid variational approach called 4D ENES-RI. This approach averages the flow-dependent ensemble covariances from the ensemble common filter, another operational system that we use at the Environment and Climate Change Canada, and also the static NMC-like covariances. And the last point here is the list of all the observations that we use, and these observations correspond to the data assimilated in the assimilated operationally. This is the ocean part of the coupled assimilation system. It's based on a NEMO CICE Orca 025 quarter degrees configuration, and the problem here is that this uncoupled to the atmosphere model is used twice. First, it is used to in the ocean data assimilation to provide the initial conditions for other systems, like for atmosphere but also for the coupled forecast. And then this system is the data assimilation system here is the Mercator Ocean Assimilation System SAM2, which assimilates the SST sea surface temperature daily, and then vertical profiles of temperature and salinity weekly, as well as the sea level anomalies from the altimeters. Another two important components here are two surface separate analysis. The first is a 3D CICE analysis, and the second one is the SST analysis based on the optimal interpolation scheme. This analysis computes the foundation SST daily, and the particular issue here is that this SST OI analysis is assimilated daily into the ocean component of the coupled data assimilation. This slide shows the coupling methods that we use to couple the models. The approach that we employed here to do this is differs somehow from couplers like OASIS, for example. It's not an external coupler that interpolates model fields and manages execution and data transfer. The strategy was to implement the coupling in the way that we would like to keep the operational suites with a minimal impact and to minimize the development and maintenance work. So we also would like to add some two-way transfer of momentum, heat, and moisture at the surface interface between the models. And we at the Environment and Climate Change Canada, we developed a method that is called GOSSIP, that stands for Globally Organized System for Simulation Information Passing. This method is used to exchange information when each model sends fields through the server of this GOSSIP protocol, and then it gathers MPI tiles on its own global grid and then push it back to each model. Then each model interpolates and remapped on the receiving grid. And this is a scheme of our first prototype of coupled data assimilation, which is weakly coupled data assimilation. Here we see that the atmospheric GEM model talks all the time with NEMO CICE model, and the transfer is executed every time step. And the atmospheric data assimilation is done 4 times a day, every 6 hours, and the ocean data assimilation is done daily. And you see the important feature here is that 3D VAR analysis of the CICE and the SST analysis, or based on the optimal interpolation scheme, they are done completely separately, and they are uncoupled. They don't have numerical models, and they influence greatly the initial condition of the ocean data simulation system. So all our forecast and data simulations are implemented within the system that we call MAESTRO, which is a task sequencer system. It's made to easily create, modify, and manage experiments. The MAESTRO system has a graphical interface, which is useful to visualize the flow of the experiment and to see the current state. The MAESTRO system relies on the XML flow definition files, and it contains also the configuration files, where the configuration of each task or node or module can be specified. And we'll also have so-called task files that are mainly the governing source scripts, and these task files make calls to data simulation system into models. We also have some log files, and as I said before, the graphical interface. So this is an example of how it looks like. Here we see the MAESTRO suite of the atmospheric data simulation. Each block, each rectangular block, corresponds to different task. And for example, here with this arrow, we see the task which is called forecast. This forecast in the assimilation stage is made to compute the 6-hour background state. And if we click on this block, we can see on the right-hand side the inner structure of this block, when we see the calls to the atmospheric model GEM and to the ocean CICE model, NEMO CICE. And the same structure is used in the block below, which is called post-assimilation cycle, which is done to compute the 10-day forecasts. This is the MAESTRO suite of the ocean data simulation. In coupled data simulation, we not only need to establish communication between models, but the data simulation systems should also talk to each other. And using MAESTRO, it's quite straightforward, because each MAESTRO suite, similar to the modules and the model nodes inside the suite, has a configuration where the suite dependencies may be set. And like this, every 24-hour cycle of the ocean data simulation, is waiting for the execution of 4 consecutive 6-hour atmospheric assimilation cycles prior to continue to the next cycle, and vice versa. The next day atmospheric data assimilation suite should wait until the ocean data assimilation computes the initial condition for that day. These are some results comparing the weekly coupled data assimilation with the current uncoupled data assimilation. This plot is to illustrate the performance of such system. Here we see the difference in standard deviation of the air temperature against the mean analysis. Is a function of the forecast lead time from 0 to day 5. And when the difference has positive values, or in red color, it means that the coupled system works better than the uncoupled one. And if it's blue, it's like the coupled is worse than uncoupled. And as we see, in most areas the color is red, so we slightly improve the atmospheric score, but the only significant improvements is here in the first 36 hours near the surface. So the result is mainly quite neutral. And this is the same result for the ocean component of the data assimilation. Here we see the ocean near surface temperature in some zonal section of the ocean temperature, and you see that sometimes it's red, sometimes it's blue. So but the differences are small and the results are quite neutral. We suppose that it's related, such performance, which is similar to uncoupled assimilation. It's related to the current state of the sea surface temperature data assimilation, which is uncoupled, and impacts greatly the performance of ocean data assimilation. That is why we are going to find some more consistent way to perform this coupled data assimilation, and we are moving towards the stronger coupling. What does this mean is that we will try to compute the sea surface temperature analysis as well as the CICE analysis along with the atmospheric data assimilation every 6 hours using the common 4D and VAR data assimilation framework, using the same software. The analysis of SST and CICE actually use the background error covariance matrix, which is computed using the diffusion operator, and both SST and CICE analysis are produced on yin-yang grids, which is useful to avoid the pole problems. And first, the first step in this development is to perform the 3D VAR daily SST analysis and to compare them with the operational system, with the current operational system, and then to import the whole 4D and VAR MAESTRO environment to compute SST and CICE analysis within this. And after everything works, we can move even further to compute the SST analysis along with the atmosphere and CICE every 6 hours. And this is an example of the MAESTRO surface data assimilation suite, which is used operation.
2 minutes, please. Sorry.
Yes, thank you. So here on the top we see the current task computing the SST operationally, and we added here some block here, the second blue block here, which compute the SST using 3D VAR and the CICE using 3D VAR. And then the work implementing the whole 4D and VAR analysis has already started and will be tested soon. These are some preliminary comparison between the current SST analysis, which is uncoupled, just isolation, and against the new 3D VAR SST analysis. You see the 3D VAR is in red and in the operations in blue, and we plot here some mean observation minus forecast statistics for SST against assimilated data on the top plots, and against Argo data, independent Argo data that are not assimilated on the bottom plots. And you see that we have some pretty improvement against assimilated data using 3D-VAR, but the comparison against Argo data are quite neutral. So it's actually a good result. So our system is stable, and we are ready to proceed to go further towards the stronger coupled data assimilation. Actually, I'm done. These are my conclusions. So we implemented the weekly coupled data assimilation between atmospheric and ocean data simulations. We show some slight improvements with respect to uncoupled data assimilation. In order to go further, we are looking for the further consistency between the systems. We are going to implement stronger coupled data assimilation, and to this end, we compute the SST inside our common data assimilation framework, which was initially developed for the atmosphere only. Thank you very much.